Hello, this is Kurt Young, Senior Technical Marketing Engineer, and welcome to Learn at Kemp, a series of videos to educate you on Kemp technologies, load balancing, and application delivery in general. This is Technical Module 1. In this module, we'll cover the following topics: topology, which includes different options to deploy Kemp LoadMaster; scheduling and persistence, which controls where to send the traffic; health checks, to ensure traffic is sent to a healthy server; and finally, transparency, which defines how the real servers see the traffic that's being sent to them. There are two configurations that will be discussed. One arm is a simple topology, where the LoadMaster and all real servers are on the same network, and 2-arm is where they're on different networks or subnets. A virtual service on a Kemp LoadMaster represents the virtual IP address, port, and all of the configurations defined when publishing an application. The topology used will determine the flexibility you have when creating virtual services. Virtual services will be explained in detail in a later module. Once again, the one-arm configuration is when both the virtual services and the real servers are on the same network. This is the simplest topology when deploying Kemp LoadMaster to publish workloads. In a 2-armed configuration, the virtual service and real servers are on different networks. This is typically used to isolate traffic to a particular network, such as a DMZ, in order to provide additional security to the internal network. This configuration also allows for server NAT to be leveraged, which will NAT the outbound traffic for real servers. We will cover this server NAT in a later module. Now on to scheduling. Scheduling determines how much traffic each server gets used. Kemp LoadMaster provides several options on how this traffic is distributed. The scheduling methods available on Kemp LoadMaster are round robin, weighted round robin, least connections, weighted least connections, fixed waiting, adaptive, SDN adaptive, weighted response time, and source IP hash. Each of these scheduling methods will distribute traffic in a different way. Round robin is the simplest method. This method will just assign real servers in order. In an environment with 2 real servers, session 1 will be directed to server 1, session 2 directed to server 2, session 3 will then be directed back to server 1, and so on. Weighted round robin will add a little bit more control by setting weight to allow one server to get more connections than another server. Least connections method will determine how many connections each server has and will send any new connections to the server with the least amount of connections. Weighted least connections works like least connections, but will take the configured weight into account when selecting the real server. The resource-based or adaptive method will periodically monitor each real server resources and direct traffic to a real server that has more available resources. Now, the resource-based SDN adaptive method leverages metrics extracted from an SDN controller to determine the best path. Fixed waiting, as the name implies, will send all traffic to the highest weight real server. Should the server become unavailable, the traffic will be sent to the next available weighted server. No 2 real servers should have the same weight, as this will result in unpredicted distribution. Weighted response time will measure the time it takes for the real server to respond to a health check. The real server with the fastest response time will be sent more traffic than those who respond slower. And finally, source IP hash. A hash of the source IP is generated and used to find the correct real server. This means that the real server selected is always the same from that host. Because this method uses the client source IP address and ignores current server load, a particular real server can easily become overloaded. Here's an example of resource-based scheduling. Server 1 is using 75% of its CPU, and server 2 is only using 72%. Therefore, the next request will be sent to server 2. Of course, all servers using the agent should have the same server specifications. The agent can be installed on Windows servers 2008, 2012, and 2016. The next core topic is related to session persistence. This is sometimes also referred to as session affinity. This will ensure that traffic from a particular client is always directed to the same real server. Depending on your configuration, persistence will override a scheduling method. For example, if round robin is configured for your scheduling method, connections from the same client will ignore that scheduling method and be directed to the same real server. A common reason for using persistence is when authentication is required on the real server. Persistence will prevent that client from connecting to a different real server, which can cause them to re-authenticate again. In this diagram, in the left you can see that without persistence, the same client has connections being distributed to all the real servers. On the right, with persistence, the client's first connection will be directed based on the scheduling method, and then all additional connections will be sent to the same real server. Now there are several ways to ensure persistence is handled properly on a Kemp Loadmaster. Source IP is the simplest approach, which will just look at the client's IP address and route that traffic to the same real server. Now there are some caveats with this method, which will be discussed in just a bit. Super HTTP is a recommended method for achieving persistence for HTTP and HTTPS services. It functions by creating a unique fingerprint of the client browser and uses that fingerprint to preserve connectivity to the same real server. The fingerprint is based on a combined values of fields within the header. URL hash will simply send requests with the same URL to the same real server. With HTTP host header, the Loadmaster will send all requests that contain the same value in the HTTP host header to the same server. Hash of HTTP query item will send all traffic with the same query item value within the query string to the same real server. Selected header will send all the requests that contain the same value in the specified header to the same real server. And UDP Session Initiation Protocol uses request and response transactions similar to HTTP with header fields that could be used as persistence. Server cookie, or sometimes referred to as passive cookie, uses existing cookies that are generated on the real server itself. The Loadmaster will observe the cookie in the HTTP stream and direct the traffic back to the proper server. Active cookie, on the other hand, is generated by the Loadmaster and unique to each user. Many of these methods can also be combined with source IP as a fallback. Hash all cookies creates a hash of all cookies in the HTTP stream. Cookies with this same value will be directed back to the same real server. As mentioned earlier, using source IP persistence does come with some caveats. For instance, in the event of using layer 4, this could lead to some uneven distribution of traffic, which makes it important to see how source IP is used to distribute traffic. When NAT is used, all clients could appear coming from the same source IP address, which will direct all connections to a single server. If the client address were to change, this could force users to a different server, resulting in bad user experience or broken sessions. When using layer 7, there's much better persistence options that will provide better balance across real servers. There's always the option to fall back to source IP should no other options be available. Not all applications or components of an application require persistence, so it's important to understand the workload that's being published. In addition, it's also important to understand what the best method depending on the network environment and workload being published. A common requirement for persistence is temporary data, such as shopping carts. Persistence timeout is important to understand on the Kemp Loadmaster. The timeout has a configuration range from 1 minute up to 7 days. This timeout clock is started when the initial connection is established. The persistence timeout value is updated if the client reconnects within the timeout period. For example, If the persistence timeout is set to 1 hour and the client starts a connection at 2 p.m., if that client disconnects and then reconnects before 3 p.m., they will still persist to the same real server. Also, the persistence record is updated to reflect this, and the persistence countdown timer is reset back to 1 hour. Now, if that client were idle for more than an hour, it's quite possible that they would be directed to another real server. Health checking is configured on the Kemp Loadmaster to ensure traffic is being sent to a real server that is online and ready to accept connections. When a health check fails, that server is taken offline and no new connections are sent to that server until such time it starts to answer health checks successfully. There are several options to ensure that the real server is healthy. ICMP can be used to confirm that the real server will respond to a ping, but this method is not the best option when checking the actual health of the application. TCP connection will check that the real server is listening on a specific port. The HTTP/HTTPS method will confirm that the web application is returning a 200 OK before it marks the server as healthy. Mail, or SMTP, can be used to ensure that the real server is ready to accept SMTP traffic. There are other options such as Telnet, FTP, POP3, and IMAP, depending on the workload and necessary health checking requirements. Certain applications have specific health checking features that can be leveraged on the Kemp Loadmaster, such as Microsoft Exchange. With certain applications, such as Active Directory Federation services, you will be required to use SNI to ensure that the real server is responding properly to the health checking. Just to take a step back, look at Layer 4 versus Layer 7 load balancing. So Layer 4 load balancing will just send the traffic back to the real server without doing anything to it. The real server will see the source IP address of the original client when using Layer 4. Layer 7, on the other hand, has a separate TCP connection from the client to the loadmaster, and then from the loadmaster to the real server. This allows the loadmaster to take action on this traffic, such as apply security rules, content rules such as URL rewriting, content switching, pre-authentication, or SSL offloading. When running Layer 7 load balancing, there's an option whether the real server sees the client IP address or the IP address of the loadmaster. This option is called transparency. The loadmaster IP address that the real server sees depends on the configuration. There's an option called Subnet Originating Request, which will present the server-side loadmaster interface IP address. Without this option, the virtual IP address will be presented to the real servers. In 2-ARM configuration, it's always best to enable SOR so that the server-side interface IP address is used. When transparency is enabled, the real servers will always see the client IP address, regardless of the SOR setting on the loadmaster. As I just mentioned, when transparency is turned on, the IP address of the client is seen by the real server. The server must send this traffic back through the loadmaster and not directly back to the client IP address. Using the loadmaster as a default gateway on the real server will ensure this occurs. With transparency off and subnet originating requests off, the source IP address of the client connects to the virtual IP address of the loadmaster, and the loadmaster will send the traffic to the real server with the virtual IP address. Now the real server will send the traffic back to the virtual IP address of the loadmaster. This is not a problem in a 1-ARM configuration when the real servers and loadmasters are on the same network, but in a 2-ARM configuration, the real server may not be able to connect directly to the virtual IP address. So in these 2-ARM configurations with transparency off, you should always turn on subnet originating requests. Now, the source IP address of the client connects to the virtual IP address of the loadmaster. The loadmaster sends his traffic back to the real server using the server-side interface IP address, and the server can easily send that traffic back to the load master. So once again, to sum it up, with transparency on, the load master will pass along the original source IP address of the client. With transparency off, or non-transparency, we'll NAT the address so the source IP address appears to be the load master. When troubleshooting routing issues, always start to look at transparency and subnet originating request. This is usually where the issues reside. If the need for transparency is required, then the real server default gateway should point to the load master. And there should be no clients on the same local IP subnet as the real servers. Okay, to remember, all layer 4 traffic is transparent. Traffic at layer 7 can be either. Non-transparency is almost always easier, unless there's a requirement to see the original source IP address of the client. Non-transparent mode will often fix routing and traffic flow issues. To look at pros and cons of transparency versus non-transparency, transparency preserves the original source IP address of the client, works with either layer 4 or layer 7. Cons: no application access for clients on the same subnet as the real servers, and the real server gateway must be the load master. When using non-transparency, you can access the application on the same subnet as the real servers. Real server gateway does not need to be the load master. Real servers can be on the local subnet or remote subnet. Cons: the source IP of the original client is not preserved, but can be added through HTTP headers. This concludes Technical Module 1.